there are four memories. You have to remember, the rat has to remember, the events that occur on the left. The rat also has to remember the events that occur on the right. And then after it's done poking its nose into that crazy hole, it's got to come back and remember the events on the left again and the events on the right during its non-net phase. So there are basically four memories. We can create, as I just showed you, we can create very good models of how these long-term memories are created, how they're formed. But if we have to create a different model for every memory, you can imagine how many models we're going to have by the time we get to the memories that are required just for somebody to get through their daily life. It's going to be huge. It'll be impossible to manage. So what we really need to do is to find a way for a model to be able to incorporate many memories, and so that we only have one system that can spit out for any given input the appropriate output. And we figured out how to do that, so we call that a universal model or a universal code. And so we can now incorporate many memories into one model. And so we can easily imagine having one small bit of memory and one small chip that incorporates many models for a patient to use. Let me just, okay, so what does this all look like in the form of a prosthesis? So here we have an animal that's performing this task, learning how to do this task, and we're recording from the CA3, that input zone, and we're recording from the long-term memory output, CA1 zone. And our model is making predictions about what the output should be in terms of a series of action potential like events, in terms of impulses. Right? And we have a mini pump. There's a pump that's inserted into the brain, into the ventricular system, and we're infusing saline into that system. After a while, instead of infusing saline, we infuse a compound known as NK-801. This is a compound that blocks the NMDA receptor channel, not the receptor, but the channel. And so what that does is to, in large part, it lowers the amount of activity in the hippocampus quite a bit, and it changes the dynamics of the hippocampus so that the output for any given input is no longer correct. And so the animal now has a malfunctioning hippocampus. And so it cannot create appropriate long-term memory, so it fails at this task. And so there's no more water for the poor little rat. And then what we did, what we tried to do was to see if our model could be used to substitute for the hippocampus, to see if we could take what we have learned about these codes and insert the codes ourselves. So these codes were codes that we had saved, and so what we did was to, now with an animal that has a very little activity coming out of the hippocampus, we used the same electrodes that we had reported from. We electrically stimulated those sites with the codes that we had reported. So for each of the inputs, we inserted the code that we had observed the animal had created with its own hippocampus, and we simply electrically stimulated those. So the way that the data looks is the following. So here's our forgetting curve, and these are for animals that receive the saline. So it starts very high with just a few seconds of delay. By the time we're in 30 seconds, it's very close to the chance. When we insert the NK-801, when we infuse that, this whole curve drops. And the animal basically at chance levels after 10, 11 seconds. So this is, now you have a picture of what the short-term memory capacity of a rat is. This is it right here. And then for these later delays, the animal is performing performing at chance or even below chance. When we use our system to electrically stimulate these codes, we bring that curve back up. So we're almost at control levels for the animal's performance, because we're inserting the long-term memories. We're putting the long-term memories into the hippocampus. And from there, they're going to the appropriate parts of the brain, because we haven't changed the anatomy. And so we can restructure or recover the long-term memory of the animal by using electrical stimulation. Now, as in thinking about this in the context of a prosthesis, it doesn't make a lot of sense to have someone control the prosthesis and look over the shoulder, basically, of the patient. You like to have this this coding process, this recovery process, happen automatically. And so we infused other animals with a smaller amount of NK801, so that not only did so that the CA1 field, the output field, that was blocked, but the CA3 field was still active. So the inputs were still active, which meant that we can record, we can extract the activity that used to be the input to our model, and we can supply this then as the input to our model. And so here's the same loss of long-term memory I showed before, but now when we take the output of CA3 and just connect it to our model, either to the chip or to the software, we get recovery of the system again. But now we don't have to watch anything. We don't have to look over the shoulder of the rat. This still functioning part of the hippocampus is connected to the model, and then the model makes a prediction as to what the spike train should be, and it puts those back into the hippocampus. And the animal can go about its daily life without us having to do anything. So we can reach a point where everything is closed loop and the animal functions appropriately. I'll skip this. We can also, it turns out, if we take a normal animal and do the same thing, that we can enhance memory function. So if we add the model's prediction, we add the model's excitation to the excitation that's generated endogenously by the rat, we actually get better memory than normal. And we've shown this in a number of ways, in a number of conditions. And I'll just say that all of this depends on having the appropriate patterns. It's not a function of just increasing the excitability of the tissue. If we just stimulate randomly, or we run every controller we can think of, and the only thing that works, the only thing that causes recovery, and the only thing that causes enhancement is stimulating with the appropriate code. If we stimulate with the inappropriate code, if we scramble the coefficients of the model, if we scramble the output, the connections to the outputs of the system, none of that works. Only stimulating with appropriate code works. So we clearly are communicating with the brain we might not understand the code, but it's clear that the brain understands our version of the code. And that's where we need to be for all this to work. I'll let this go. You don't need, I'm sure you don't need to know about the microchip version of this. I'll just say that there is a microchip version of this. It's almost complete. Much of it, we're into the third or fourth generation, and it's almost at the point of operating completely. So we will be able to realize something. This is just 6 millimeters, so we will be able to realize something that can fit on the top of even a rat's head, let alone a human's, that can take perform the function of the models as I've described. We want to do this for humans ultimately. I'll just say that we're moving into the monkeys. Here it's the same kind of task where we show the monkey stimulus, show the monkey a pattern, there's a delay period, and we show the monkey several patterns, and he has to select which one he saw before. So it's a delayed match just happening, but it's the same idea. And we're now working on new recording systems to reach the hippocampus, because it's in the non-human primate and in you and me, the hippocampus lies in the temporal lobe, and so it's very far below the surface of the skull. So it takes a new kind of electrode design, and we're trying that out right now. We've done a lot of work, I know I'm over time, so I'll just say we've done a lot of similar work in the prefrontal cortex, and here we can discover the same kinds of memory codes. The prefrontal cortex, the memory codes relate more to execution of the memories, how the memories are ordered, so that an executive function that accomplishes the goal can be attained. But we've been able to identify some, instead of the hippocampus is very sensitive to the stimulus, to what needs to be remembered, what its features are. The prefrontal cortex has more to do with this executive function, which is related more to behavior. But nonetheless, we can, in looking at the processing in the prefrontal cortex, by looking at the inputs in layers 2 and 3 and the output in layer 5, we can perform the same kind of multi-input, multi-output model. We can make predictions about how the input patterns should be changed to the output patterns, and we can enhance, we can enhance memories that depend on the prefrontal cortex. So the same strategy works in monkeys as well as in rats and in other brain areas. I'll just mention the fact that we're working with Charles and with Christy on a project that involves recording from human hippocampal slices in an effort to improve the system that Christy's working on that uses electrical stimulation to suppress seizure activity. And in the process of learning more, I'm learning more about what the human hippocampus is all about. And we are learning more about where to put electrodes so that we can perform the same kinds of experiments in humans where we look at the spatiotemporal patterns of activity in the hippocampus to understand what kinds of codes for memories are created within the human hippocampus. So it's a lot of fun working with these folks. I think we're going to get quite a ways very quickly. So, of course, there are lots of people, some of them I'm sure that I did not put up there who should be up there, but it's a great team from across the country and from many different labs that have helped to put all this together, and funding that comes from a number of sources that, of course, we can't do without. So with that, I hope that was a reasonable overview. Gives you some idea of how we're trying to approach prostheses for cognitive functions, and we hope to get there soon. Thank you.